Let's turn now to the task of isolating the portion of rainfall that feeds relatively rapidly into the stream and produces the observed stream event flow, the portion of the discharge that comes from the precipitation event. A graph of precipitation versus time is called a hyetograph, and here's what a typical one looks like. You're plotting the precipitation rate here, length per time, typically, versus time. And if we do that, then the area under the hyetograph, this area here, corresponds to this area here. It corresponds to the total depth of rainfall that falls during this time, depth of precipitation. So this might represent, if we're measuring precipitation rate in inches per hour over this period of time, then the area under this hyetograph would be in terms of inches of rainfall. We could, if we wanted to, actually get the volume of rainfall that falls over the entire watershed by multiplying this depth times the area of the watershed, and that would produce a volume. And that's sometimes what we actually end up doing. But it's a really important point here that needs to be made, is that when we apply this approach that I'm going to describe now, what we usually assume is that the precipitation that falls on a watershed or catchment is the same everywhere. In other words, we can describe it with just a single hyetograph that applies everywhere. And so if we want to know, we don't have to worry about Thiessen polygons or the isohyedral method or anything like that. We just have a single hyetograph that represents precipitation over the entire watershed, and we can use that to figure out how much of that precipitation then is going to relatively rapidly make it into the stream. And that's what this little video is all about. How do we actually figure out what portion of this total precipitation is going to be able to get into the stream relatively rapidly? Now, even though in reality a hyetograph looks like this, in practice, they actually sort of look something like this instead. And the reason for this is that historically rainfall data have been collected and reported in time increments. Maybe let's say this is 1 hour, for example. So instead of having a continuous record of precipitation during the storm event, what we have are sort of sum totals over fixed increments of time. And that creates a bar graph approximation to the real hyetograph, which might look something like this. It doesn't really matter because the idea is the same. We want to calculate this effective precipitation from the total precipitation by removing what are called the losses. And the losses are those parts of precipitation that don't make it relatively rapidly into the stream. The losses include evapotranspiration, canopy storage, depression storage, and infiltration. And some of these we can kind of neglect or ignore because they're not going to turn out to be very important. For example, we normally just eliminate or don't consider evapotranspiration because this is a rainfall event and the relative humidity is probably close to 100%. And we know that when the relative humidity is 100%, you don't get any evaporation at all. Similarly, canopy storage we usually ignore simply because it's usually a really small thing and it happens very, very quickly during the very first part of the rainfall event, and it doesn't usually account for very much of the total precipitation. Depression storage, on the other hand, could be important, but we just don't know very much about it, and we have a real difficult time actually measuring it or figuring out or predicting how much it should be. So honestly, usually we just sort of lump it into sort of general losses. The big one though that we really need to worry about is of course infiltration. We know that as water falls, if we can imagine, for example, a very light rainfall falling, right, most of that water, maybe all of that water, would initially just seep into the ground and hardly any of it would run off to become event flow in the stream. So if infiltration is the big thing we need to worry about theoretically when we think about the losses. Now, when we think about infiltration, we immediately should realize that a big factor in the degree of infiltration is going to be the antecedent moisture conditions, right? So if the soil, for example, is already saturated at the beginning of the rainfall event, then it can only absorb water at a very small rate, and a large proportion of that precipitation is going to end up rapidly entering the stream. And on the other hand, if the soil is bone dry at the beginning of the precipitation event, then it will have an enormous capacity to absorb water, and maybe hardly none of the precipitation will end up rapidly flowing into the stream. So when we're dealing with the biggie here, infiltration, a huge factor that we need to take into consideration if we want to do this rigorously is the antecedent moisture content of the soil, okay, of the soil. Now, the problem here is that in many cases we really don't know this. So if we really want to do this rigorously, there's a lot of things that we don't know very well. We don't very well know depression storage, the amount of depression storage, and we probably don't really know very well what the antecedent moisture conditions are of the soil, and certainly not what they are of the soil all throughout the watershed, let alone even at one place. That's a lot of data that we probably don't have when we try to do this exercise, and that will affect the way we actually typically attempt to do this separation. Well, how do we actually go about then separating the hyetograph? And there are actually three sort of basic approaches that are used. The first approach would be to do this rigorously using computers and theory. We'd have to know the antecedent moisture conditions, we'd have to know the distribution of rainfall over the watershed, and if we knew all that and we really knew the runoff generation processes, we could in theory calculate how much of the runoff will make it into the stream quickly. But as you might suspect, this is enormously difficult to do, and in fact has only really been tried in a sort of research context where you're trying to understand something in a small watershed and you're heavily instrumenting it, and this is not something that is generally done if you want to separate the hyetograph for the reasons that we talked about at the beginning of the last video. So although this is really the best way to do it, in fact, we never in practice really have enough data to actually do this. The second approach is sort of like the way we do stream hydrograph separation. We apply what's called the rational method, which is to use some kind of simple assumptions that may or may not be correct theoretically, but at least they sort of work. For example, one possibility could be that for each increment of rain, we can assume a constant proportion of effective precipitation. So for example, during this first one here, maybe it's 50%. So we could assume that the effective precipitation is going to be, I'm going to, hold on, let me fix this here. So I'm actually going to assume that what I'm actually drawing here are the losses. So the losses are everything underneath these lines. So about 50% during each interval of precipitation is lost, mostly to infiltration, leaving behind the rest to become effective precipitation. Another, perhaps more justified approach might be to assume a constant infiltration rate over the entire duration of the rainfall event. So maybe the constant rate is sort of like this. So this is the infiltration rate, and it's constant, right? And so anything that falls below this is going to be lost. And so here this entire precipitation event is lost, the interval is lost, and the losses then are shown below the line, and everything above the line represents water that is precipitation that is rapidly flowing into the stream. We could also make the assumption that the infiltration rate is going to follow sort of what we know an infiltration curve looks like. Remember, an infiltration curve starts out high and then decreases after a couple hours, maybe to a constant value like this, right? So we could say, okay, we're going to assume, and again, we don't really know exactly what this is going to look like, but we know what its shape ought to look like if the soil isn't saturated, and we can assume therefore that the losses represent mostly infiltration, and anything that falls below that line would be a loss, and we can then simply just take the part above the line to count as the part that's getting to the stream quickly. Now the third method is actually the one that's done most commonly, and it's really quite simple. It's to assume that, just sort of back calculate it, because we know that by definition the amount of the event hydrograph, the water in the stream that comes directly from runoff and not from base flow, has to, by definition, equal the effective precipitation, right? That's by definition. So if we work from the stream backwards, we take a look at the hydrograph from the stream and we separate the hydrograph from the stream into base flow and event flow, then the event flow here must by definition equal the effective rainfall distributed, summed over the entire watershed. So we can take the precipitation rate, we can take the total precipitation, maybe this is, for example, this is, let's say that's 1 inch of precipitation, right? And we can take the, we can take the entire, I did this wrong. We can take the entire volume of water, the depth of water from the hyetograph, multiply it by the area of the watershed to get the total volume of water added by precipitation. And we know what portion of that rapidly flowed to the stream. That would be equal to the event flow of the stream. And therefore, we can then back calculate how much of that precipitation must have infiltrated in the soil or be lost in some other way. And we can calculate a ratio of the losses to the input precipitation and separate out the hyetograph that way. And actually, that's probably the most common way to do it, because the other methods require either too many just unjustified assumptions or way too much previous information that we simply don't have.